So I think we have done the potential energy, right?
Yes, sir, we have.
And we have done the condition for conservative force as well, right? So what is the condition? What is the mathematical way to kind of verify that whether a given force is conservative or not? So we know that I think we have done this, but let me just confirm. For conservative force, del cross F equals to 0, right?
Yes.
Because we proved that F equals to minus del U, where del was. Now, this is slightly advanced, so you can skip this part if you're not able to not to worry at all. So del is like an operator or del operator. And to verify whether a given force is conservative or not, if it is given in the IJK form with variables. So we just check. So we calculate the determinant, and if the determinant turns out to be 0, we say it is conservative. So if a force is constant, it is by default conservative. If I say F equals to 10I, which means I am fixing the magnitude and direction both. So any constant force, any constant forces conservative by definition. Okay, and I think we have done all the remaining property of conservative force, right? Is that done? Is it done? Hello,
Yes.
everyone. You can just check the last lecture notes. I think you guys don't think that. Last lecture. Have I shared the last lecture PDF?
Yes, sir, you have.
Yeah, we have done this part. Yeah, up to this part we have done. Correct. So let's do some example. If I give you U equals to x square y plus zxy plus z2 square y square. It's a potential in a three-dimensional space because the dependency is on all the coordinates, which means it is three-dimensional. The moment you see potential as a dependent on only one variable x, it is one-dimensional force. If it is two-dimensional, three-dimensional. So the force you may get one dimension, two or three-dimensional or okay. So now the idea is find the force at 1, 1, minus 1. So at a coordinate for 1, 1, minus 1, what is the force present? So how to do that? So to find the force, first you need to find each component separately. And once you differentiate, so the differentiation is minus del U by del x, so you differentiate with respect to x only. Okay. Okay, Siddhant. So now you know how to do this.
Yes, sir.
So do and tell me the answer.
So it is fx minus 2.
I need to check. I just need to check. I'm sorry.
Yes, sir. -2.
Minus 2. Okay, great. So minus 2xy, yz, and if you put 1, 1, so 1, 1, 2, minus 1, 1, and 1. 2, minus 2 is the right answer. Very good. So similarly, can you find the FY and FZ?
So fy also minus 2.
Okay,
Yes,
very good. Very good. And what is FZ then?
FZ1.
So now the force we can write as minus 2y minus 2j, yeah, minus q. Okay. And the modulus of force we can get is under root of
So plus K gamma.
plus q, right? Yeah, plus q. Right? So it is 9, which is 3, right? So
Yes.
you will be asked question like this in JEE-Mains. All right. So we are done with the conservative and non-conservative force. Now we can talk about the equilibrium of particle under action of conservative force. So equilibrium of particle under action of conservative force. Yeah. So I'll do 3 situations. So you can see there are 3 situations. I can just make it one size. And now imagine we have a ball, and the ball is kept at the point where it is at rest. So this is called the point of equilibrium. If I keep it here, will it be at rest? Is it possible?
No, sir.
No. Similarly, on this inverted wedge, the only point where it could be at rest is the topmost point. If you move it slightly left and right, it will start falling, right? But on a
Yes.
flat surface, it can be at rest anywhere, right?
Yes.
Yes.
So the logic is, in the very first case, the object is at the bottommost point at rest. So if I take this as a reference, can we say it will have the lowest potential? So the U is minimum. But for this scenario, this is the maximum potential, isn't it? So if it will start moving, the potential will decrease or increase for case 2. For case 2, what do you think?
Will decrease.
It will decrease. But if you can see the case 3, if you start moving, if the ball starts rolling on the plane, the U remains
Same.
same, constant. Very good. So in each case, force is 0 because it is at rest. And the F here means net force. And F is defined as, let's think as one-dimensional equilibrium. So when we say F is del U by del X, and if I say F is 0, which means okay, I'll make it D because it's one dimension. So du by dx becomes 0 for one dimension. For a single variable function, we can use the exact differential instead of partial differential. So the rule is simple. If it is one variable function, we can use the exact differential. If it is multivariable function, we use the partial differential for each component. Now you can also see the U is minimum. Now how to find the minima of a function? How to make sure that the function is attaining the minimum value? So we do the second derivative test, right? And for second derivative test, if it is positive, we say it is minimum, right? For local minima, the second derivative must be positive. Do you remember from calculus?
Yes, sir.
Yes.
Here, the U is maximum, which means du by dx is certainly 0 because force is 0, but the second derivative is negative. In the third case, first derivative is 0 because anyway U is constant here, and second is also 0, no matter what we do. So now let's try to displace a bit and try to understand the motion. In the case 1, if I displace either right or left, what will happen? It will feel the restoring force. Of force will try to bring it back to the mean position, right? So the gravity will let you come back to the old position, isn't it? So if you displace slightly right to left, what kind of motion will happen? Tell me.
Sir, oscillatory.
Correct. So it will perform the oscillatory motion. Whenever there is the oscillatory motion, it means it is trying to come back to the mean position, or it is trying to go back to the position of rest or equilibrium. So such equilibrium is called stable equilibrium. So this is called what is the important point of stable equilibrium? You can see something very easy. The word equilibrium means net force is zero, which we have proved here. This means equilibrium. So what defines the stability? Stability is defined in terms of potential energy. And you can see that the potential is attaining the lowest value. So when I say stable, it means when F is zero and U is minimum, when F is zero and U is minimum, we call it stable equilibrium. Is this clear?
Yes.
So when F is zero and U is minimum, we call it stable equilibrium. Understood? Now, if you come back to the, okay, we'll continue for the first case. In case of stable equilibrium, we may see oscillation. So I just mark it. So in this case, upon displacement from mean position, particle will have tendency to what? I hope this is clear. Tell me, everyone.
Yes.
Yes.
Okay. So in the first case, things to remember for stable equilibrium, there are two conditions: that du by dx is zero, and the second derivative is positive. And the chance of a system is only possible in this case. In the case two, what will happen? In the case two, if you displace slightly towards right, what do you expect? What will happen? Siddhant, tell me.
So it will roll down.
So it will continue moving in the direction of displacement, right?
Yes.
So no stability. When we say no stability, will continue in the direction of displacement. Okay. Hello. Is this clear?
Yes.
So no stability means no oscillation, no oscillating, no oscillation, no oscillation. And the potential is how much? Maximum. So whenever a system is in its maximum potential configuration, it is highly unstable. That's logical also. So stability is always talked about in terms of energy. So this is what you should remember. The same idea you do apply in case of what? Chemistry. So you talk about stability, talk about energy, isn't it? And we know that in the lowest energy configuration, the system is most stable, right? So any configuration which offers you the least potential will be most stable. And if you try to disturb, it will try to go back to that configuration. And therefore, it will develop the tendency of resistance or oscillation. Is this clear, guys?
Yes.
Yes, sir.
Now, case 3 is but obvious. It is called neutral. So it is neither stable nor unstable. Because if it displays from A to B, it will attain the new equilibrium at B. So it is happy everywhere because it is neither losing nor gaining some potential, which means it is neither moving towards the stability nor moving towards the instability. So every portion is equilibrium position. So this is called neutral equilibrium. So this is called stable equilibrium. It's called unstable equilibrium. And this is called neutral equilibrium. Is this clear? It is clear.
Yes, sir.
So in case of neutral, nothing will happen. So what we say here, in this case, body remains in its equilibrium position. In this case, body remains in its equilibrium position even at displaced position. I hope this is clear to all of you.
Yes, sir.
Is this clear? Oh. Yeah. So we are done with the idea of stability and instability and neutrality. The idea of equilibrium. We'll do some question. We'll try to find the equilibrium position. So we have something called Leonard Jones potential. This is very crucial. We will come across very often in chemistry, physics, everywhere. So this potential energy you must have seen somewhere. If you have any textbook, you can't miss this graph. It is a graph between the potential energy and the separation between two H atoms. So we have H2 molecule in which we have H at some separation called the bond length, right? So bond length is an idea at which we say that it is the separation at which the energy of the system is minimum. This is the lowest energy configuration. So the separation at which the system attains the lowest energy configuration is called bond length. Do you know this?
Yes, sir.
Hello. So what is bond length? Can you explain? It is the separation at which. Hello.
When it attains lowest energy configuration.
Okay. So the force will be zero at that position. At any equilibrium position, what happens? Lowest energy is always the point of equilibrium, isn't it? We can also see the lowest energy by default is point of equilibrium. Do you realize this?
Yes, sir.
Yes.
So whenever you attain the lowest configuration, you also attain the equilibrium. Okay. And at equilibrium, the net force is zero, which means the attractive and the repulsive force both are zero. I mean, both are balancing each other. Attractive and repulsive are cancelling each other's effect, which is like very interesting position. It's like if you try to bring them further closer, they start repelling. And if you try to remove away, you start attracting. Is this clear what I'm saying?
Yes.
So net force is zero doesn't mean it will be like you can take it away. The moment you try to separate the H atom, they start attracting again. And if you try to even bring even much closer, the repulsor will be dominant. Why the repulsion is dominant? Because of the obvious reason. Every atom will have nuclei which is positively charged, and electron which is negatively charged. At large separation, they mostly attract. So the attraction is a dominant feature. The reason being the two nuclei do not repel at large separation. They are short range force. They are powerful but short range. Okay. They are very powerful but short range. So what happens if I bring it closer? So the two atoms kind of their orbital will kind of recombine. This is called the MOT theory, right? You know MOT? Molecular orbital theory.
Yes, sir.
And we have LCO, linear combination of atomic orbital. So the linear combination of atomic orbital. So it is no longer the atom orbital, it is the orbital of the molecule. Now what happens? They do repel like this, but they only repel when they come really close. So when they attain the lowest energy configuration, then the attraction of the negative and positive charge pairwise and the repulsion between the nuclei will balance out each other. And a formation of molecule is always accompanied with the lowest energy configuration. It means when you form the molecule from the atom, in the due process, you release lots of energy. And the energy release is called the binding energy. It will hold them together. It's binding them together. Also called the bond energy. So if you want to break it into, give back that energy. The energy which I released in the formation. And if you want to break down again into atoms, you have to supply the energy. Is this clear, guys? What I'm saying?
Yes, sir.
Yes, sir.
So how the graph will look like if you try to plot it. If you plot it, let's say if the separation is too large, they don't interact at all. When we say the energy is almost zero. But as you bring them closer, the initial force will be attractive or repulsive. When the two atoms come
Attractive.
closer, the first force they feel is attraction. Repulsion comes only if you come very close, not far. So because of attraction, the energy will decrease or increase. You are going along the force of attraction by going closer, isn't it? Okay. Hello.
Yes, sir.
So the energy will decrease like this. And at some point it will become minimum. But beyond this point, the repulsion is the dominant feature, so it will again increase the potential because you have to work against the repulsion to bring them closer. Having zero separation means infinite potential. So you can see clearly something interesting here. This is the point of lowest potential. So the graph shows that at this is the separation R not is called the bond length. And at this length or separation, the energy is lowest. And you can also see that if I draw a tangent, what we'll get? You guys. A tangent at this point will be parallel to the x-axis, isn't it? So du by dr is how much? 0, right?
Yes, sir.
And by definition, force is minus du by dr, so it is also 0, correct? So if the slope is 0 of UR graph, then say the force is also 0. So whenever the slope is 0, force is 0. It is clear?
Yes.
Therefore, I mean, you may be asked to find the in a UX graph the potential points of equilibrium. So if I draw a graph like this, let's say some hypothetical situation. Some random hypothetical situation. You can see how many tangents we can draw parallel to the x-axis. 1. So for the given graph, we can draw 3 such tangents, right?
Yes.
So the force is 0 here. So how many points of equilibrium do you see?
So 3 points.
So number of points of equilibrium. So how to identify the points of equilibrium in a US graph? By looking at the crest of trough, right? And it is very easy to count. These questions come in the bit side and JEE-Mains also. Very easy. Just you need to know how to read the graph. And we have something called FX graph. Now, by looking at the force and the X graph, you can also find the equilibrium nature. So how many points of equilibrium do you see? Points of equilibrium here.
1.
So 1.
Points of equilibrium, beta. How many?
So 1.
Points of equilibrium is it is the force and displacement graph, isn't it? This is force.
So 2 points.
And what is the meaning of equilibrium? Tell me.
So when force is 0.
So at how many places you see force to be 0?
So 2 points.
X1 and
X2.
So x1, x2 are x1, x2 are points of equilibrium. Okay. Understand? x1, x2 are points of equilibrium. So which point is stable and which point is unstable? Tell me. Analyze nature of stability at x1 and x2. No idea? So let me tell you the meaning of the graph. This graph is very interesting. First of all, you can see a part of graph is below the axis and the part is above the axis, right?
Yes.
Okay, so the meaning is you can see the graph is having some positive part. This is positive part, and below is the negative. Negative and positive will have meaning actually. It's a one-dimensional force. So positive means towards right. So this is positive direction, and this is your negative direction. Okay. So you need to understand something. This is the point of equilibrium. So at x1, this is a graph. We'll do a part of graph to understand the logic. What you can realize that force on the right is acting which direction? Right. Because it's positive. But force on the left is acting left. Do you realize this?
Yes.
or no? So this is the point at rest, but the moment you try to, so here there is no force. Exactly at x1 is there is no force, which is very interesting. The force only develops once you go right or left. But if you try to go, if I displace slightly right and release, this force will take you right only. Will never let you go back. And if I displace slightly left, it will go left only because of this force. It will never come back. So x1 represents what? is stable or unstable?
Stable.
Is it stable? If I displace right, you are going the right only. And left, then left. You are never coming back, right? The tendency to come back is there, yes or no?
No, sir.
Do you understand the meaning of stability? It will have the tendency to retain the position. That's why you're stable. So here, if I displace right, it will go right to left.
It's right.
So is it trying to come back?
No, sir. So unstable.
And yeah, so if I displace left, then
So it will go left.
which means again, no nature to go back, right?
Yes.
So this is not stable, this is unstable. But if I take the other case, the x2. At x2, there is no force because it's 0. But if you draw the graph, the direction of force on the right of x2 is left. And direction of force on the left of x2 is, so it is like it is squeezing back to the mean position, right?
Yes, sir.
So if you try to go left, the force will try to bring you back to x2. If you try to go right, it will again do the same. So x2 represents which position?
Stable.
So this is
Stable equilibrium.
equilibrium. Do you realize this? Yes or no?
Yes.
So you were thinking this point is the maximum force. How it is equilibrium? Equilibrium means force is 0, which is checked here, right? I hope this is clear now, right?
Yes, sir.
So this is all about work and energy. You know, the only thing that is power. Power. Okay. I can see this. So last concept is power. So you can go and study about power. Power is something which will come across in JEE-Mains very often. Power. So what is the definition of power? A rate of doing work is called power. So there are two types of power. You can define instantaneous power, and the other is called average power. Okay. Very simple. What is the instantaneous power? What is the instantaneous power? You define in differential format. You say dW by dt. So what is the average power? Delta W by delta. Okay. Now, work, elementary work is defined as F dot ds. So dW by dt is how much? F dot ds by dt. Okay. So by definition, what is called ds by dt? E is
Velocity.
your velocity. So you can see that instantaneous power depends on the dot product of force and velocity, which means you may write as FV cos theta, which means F cos theta into V, or F into V cos theta, which means if we know the direction of velocity, so let's say this is the direction of velocity and this is the acting force at some instant. The component of force which can generate power is the cos component. The sine will do nothing. So if a component is perpendicular to the velocity, it will not deliver power. So only the parallel component can deliver the power. So there are many situations, and if you cannot deliver the power, it means you can't do the work. The rate of doing work, if you can't do any work, because you can't do any, you can't transfer the energy, you don't have the power. So if you think of any oscillating pendulum, very often this question is asked. And if you look at the tension force here, if you look the path of the oscillating bob, the velocity vector is always perpendicular to the tension, isn't it?
Yes, sir.
So the power due to tension force is how much? Which means for any oscillating object, the centripetal force never imparts any power. That's logical also. It is not imparting any power because the T and the V are mutually perpendicular. So no question of power. Okay. Yes. So power is like you have a source of energy and you decide to transfer it to someone at a certain rate. So power is generated by only someone with source of energy. For example, in our car and bike, we have source of energy called the engine. The engine generates power by burning the fuel. But engine is not capable of moving the car. It is only creating the power, the energy requirement. So it is very interesting to know that when you ride a bicycle or drive a car or a bike, a motorbike, it is the friction which will let you move forward. But do you know friction never gives you the energy to move? So when you are bicycling, can you tell me from where you derive the energy to move it? Tell me. So when you're bicycling, you use your own body metabolic reaction energy. You use your own muscular energy. So the energy you consume is from your own body actually. So friction will support the motion. It doesn't mean it will give you the energy for the motion. Now that's very interesting and counterintuitive. So I'll give you example. You overcome this difficulty. So let's say your parents are providing your school education or your home tuitions or this online lectures by paying to the respective teachers. So they support your education by financing your education. But are they teaching you or we are teaching? So you can understand that the person who is supporting the motion is not causing the motion. But the person who is causing the motion is not supporting the motion. I mean, not giving you the energy to do so. So when you ride a bicycle, what happens? The energy part, you meet the energy need from your own body. But when you're driving a car, the energy need you fulfill with your petrol or diesel, or maybe hydrogen nowadays, or battery also. So these are the energy providers. They fulfill the energy requirement. But of course, it is the friction which will let you go forward. And these things are really counterintuitive. Do you realize what I'm saying?
Yes, sir.
So power means what? I mean, I gave you energy. Some agent is trying to give energy per second, some value. So you energy per second is energy, I mean power. So let's say if I say you have a bulb with 60 watt. 60 watt means 60 joule per second, which means if you switch on the bulb under the specification of the voltage, so then the bulb will consume 60 joule of energy in 1 second. So if you run the bulb for 1 hour, it will consume 60 into 3600 joules. So that is the idea of energy. So in case of home appliances, everything comes with the predefined power rating. If you buy a toaster, a geyser, or microwave, a refrigerator, they have predefined the power rating, which means how much we consume per second is known, well known in advance. So when you buy a 2000 watt, let's say mixer grinder, it's very powerful. So if you run the mixer grinder only for 1 second, it will consume 2000 joule. So imagine making some sort of chutney has consumed lakhs of energy, lakhs of joule, isn't it? So even if you run your mixer grinder for 5 minutes, how much energy consumed? 5 into 60 into 2000. How much? So 1, 2, 5. Is it correct? Six lakhs joule. So sorry, for 5 minutes of mixture grinder will consume this much joule of energy. Do you know this? And how much you pay, you know? In Mumbai, you roughly pay 9 rupees for 1 kilowatt hour. You know what does it mean? It means 1000 watt hour. Which means if you use 1000 watt of appliances together for 1 hour, you need to pay 9 rupees. Okay, so while making the chutney, you only consume 5 minutes, which is 1 upon 12 hour, right? So you have consumed this much rupees. The cost of the chutney is roughly how much? 3/4. Oh, 75 paise. Right? So you roughly you need to pay 75 paise if you run the mixture grinder for 5 minutes. But this is on a very ideal estimate when we take the efficiency to be perfectly 1. But in real life, it is not so. So no device works in the same way. So you end up paying more than what you expect to pay. In fact, you can count the entire bill by calculating the appliances watt rating and using this formula. Anyway, you're going to study this thing, current and electricity. Is clear?
Yes, sir.
Okay. So power is this. So in case of one dimension, if a block is applied by the force of and is moving along this line, which is x-axis, the theta will be 0, right? In such case, the power will be either plus FV or minus FV, depending on how it is moving. So if it is going this way, only FV, right? So more space. So the instantaneous power is how much? So dW we can write as P dt. Now we put the heading first. The relation between instantaneous power and average power. So dW we can write as P dt. So we know that total work done is integration of P dt. So we can say average power as T by T. That is the in a general definition of average and instantaneous. We have done this very often in various places. I should write it here. Okay. It's clear. Am I audible, guys?
Yes, sir.
Yes.
Okay. So what kind of question you can expect? So let's say a block of mass M start from rest. A block of mass will start from rest. Okay, that's good. And it is acted upon by a force which generates constant power. Now, what is interesting to know, the power is constant. Let's quickly know. Now, try to understand this fact. What is the definition of power in one dimension? Force into velocity, right? And if F into V is constant, so as the V will increase, the F must decrease.
Yes.
So a constant power in this case is actually representing a decreasing force. So the agent is trying to manipulate the force to keep the force power constant. And what is the meaning of power? You always supply equal amount of energy, isn't it? Per second. So if you give energy to the block will speed up, right? So in time t, how much energy will supply? So a block of mass when starts from rest is acted upon by a constant force. Okay. So the idea is, acted upon by a force which generates constant power. Is this clear?
Yes.
So find the relation between displacement versus time. So what is the relationship between displacement and time? I want the S and T relation. Can you do it? And if yes, then how you going to do it? Okay. Tell me in time t, how much energy will provide? Because power is constant, so energy supplied. See, power is the energy per second. So to know the energy in a given duration, just multiply it or integrate it if it is variable and multiply with time if it is constant. So energy supplied in time t, you can write as V not into t, right?
Yes, sir.
Now the idea is if this is the energy you have supplied, how the block will exhibit this energy. So energy supplied is equal to the kinetic energy of block. Block will have only one energy, which is kinetic, isn't it? And this we know is P not into T. So we can get the direct relation of V and T. So V square is how much? P not 5. So it's clear. So V is how much? And V we can write as ds variable. Yes. So ds is just integrate. See how much? See how much? Okay. Is this clear? How this question is solved?
Yes, sir.
Now, if the in case if power is variable, and there is one more method I'll just show you. This is slightly easy. Now the next one is slightly difficult. So P naught by definition is F into V, but F we connect as mass into acceleration. And then you connect as AS dV by dt into. So basically V dV becomes, and if you integrate, you get the answer. 0. And just So I think beyond this, it is similar, right? You can see it's the same answer. I thought you guys must have done this. See, this is what we
Yes.
did here, right? This is easy one. Like logically, we know this is the answer, and we know the energy is equals to half mv square. So from here onwards, you can proceed the way you want. Now, there are various questions that will come across in power. So let's say a normal question. Let's say we have a pulley and someone is pulling a bucket of water using this thread. So you're pulling this thread by a force, and it is going up with constant velocity. And let's say the mass of the bucket is a. So what is the power of the person F? I mean, the person who's applying the force F. How much power he is generating? So it is the same answer. Power is the force into the velocity or point of application of force, not the object. So if you consider the point of application here, you can clearly see something that this point is moving with what speed, V, right? Power
Yes.
is only F into. Okay. And because it is going with constant velocity, so even F is not given. You know what is F? What is F here?
mg.
Mg. So it is mg. Okay. Now, this is the case one. If you are pulling with constant velocity. And if I say case two, if bucket is accelerating with constant acceleration A, and the instantaneous speed is V, find instantaneous power. Find instantaneous power. So in that case, the answer is same. F into V. But what is F? So you know that the bucket is, if the bucket is accelerating, can we say F equals to mg? Tell me, anyone. As we know, the bucket is accelerating. So how to get the tension? Now F is same as tension, that's for sure. F is same as this is F1. So the power in this case will be T into V. But what about the T value? What is T here?
So T minus mg is equal to ma.
Correct. So T is mg plus, right? Hello, it is clear.
Yes, sir.
So this is the power, and I can give you one more question. So let's say we have a car. So we have a car. Okay. The third example. This is very interesting. If a car is accelerating with axis of A, okay. So what is the power generated by the engine if the instantaneous velocity is V? So car is accelerating with acceleration A and instantaneous velocity is find the power, I mean instantaneous power basically generated by engine. Okay, so now the interesting fact is car is accelerating because of the friction. But the tires will create the static friction. And static friction will act only at the point of application, which is not moving. So now that is difficult for you, but you should remember the fact that work done by static friction is zero when the surface is fixed. If one of the surfaces is fixed, it is always zero. If one of the surfaces is fixed, it is always zero. So let's say remember this. Now, because the friction will not do the work, but you are accelerating, so your velocity will grow, which means your energy will grow. So from where the energy will come? Any idea? No idea. The energy comes from the engine actually. So the fuel burning and the production of energy is coming from the engine. So the role of the engine in a car or bike is to provide the energy, to give power actually, energy per se. But every car comes with some limitation of power. So you know there is something called BHP. BHP is the commercial unit of power. You know BHP? Have you heard this name?
Yes, sir. I've heard of it.
BHP. It is from the British horsepower. British horsepower. Okay. So the idea is we need to find the kinetic energy. The kinetic is F S equals to mass into acceleration. You may write like this. This is Newton's laws of motion. Nothing to do with the energy and power. But power here is very interesting. The only source of energy is engine only. So the power of engine will be the rate at which we are trying to generate the kinetic energy. So the energy is coming from the engine only. So power of engine is the rate of change of kinetic energy. Do you realize this? Hello, hello. Hello,
Yes.
hello. Okay. So kinetic energy we write as half mv square. So dk by dt will be 1 by 2 a mass is constant for the car. Assuming the petrol mass is very small compared to the mass of the car. So the mass is changing, but insignificantly. So we are not taking that dm by dt down. But in case of rocket, the dm by dt becomes really significant, right? Because we burn lots of fuel while launching the rocket, if you know it. So there, the dm by dt will not be insignificant, but rather significant. So we're going to just 2v dt by dt. So let's cancel. Now by definition, d by dt is what? A, right? And interestingly, this we can write as f is into. Now this is numerical equal, but the problem is the moment I write like this, you may end up thinking that friction is giving the power, which is the wrong notion. You need to understand that friction is not the supplier of energy. Supplier is the engine actually. So FSB is the numerical equivalence. FSB is the numerical equivalence. Understood?
Yes.
Does it mean it is giving the power? No, it is not giving
No,
the
sir.
power. Okay, so the car motion is really interesting. Now, in this case, I haven't considered the drag. So no drag. But in a reality, let's say you're driving a car. In actual terms, we'll try to understand what exactly happens when you drive a car. So we have a car. Some like that car. So in reality, we always have a drag force due to the air resistance. So let's put the drag force F. Now in JEE syllabus, they may say that the drag force is constant, but in Olympiad or maybe when the JEE becomes really difficult, they may tell that drag is proportional to velocity also. They may take the drag as square of the velocity also, but we are going to take the drag as constant force, which is not very realistic case, but to solve question, I am going to take it. So this is the drag force. Of air. And definitely the friction will act like this, and our friction will be static. A is the instantaneous acceleration, V is the instantaneous velocity. Okay. If it is so what you can say? Laws of motion, Newton's laws of motion, postulated laws of motion. Fs minus drag equals to mass into acceleration, right? Can we write like this? Can we write? Hello. It is clear.
Yes, sir.
So the friction is the sum of these two, right? So this is very interesting. Now drag force will take away the energy, will do nothing, will give energy. What do you think? What it will do? What it will do?
So we'll take away the energy.
It will drag is always opposing your motion, so it is going to take away the energy because the velocity and the drag force will always act in opposite direction. Friction is static, it is not moving along with the wheel. Friction is acting at a place and then it is over. Then new friction is coming, then again over. So what we need to realize that the drag force, the work done by drag force is negative. Like it. It will take away the energy. Okay. So how we write the scenario? So what happens is the engine will have to provide two energy. Power of the engine is like not only you increase the kinetic energy of the car, but you also work against the drag force. So drag is eating away the energy at this rate. So the engine will provide both energy, this and this. So the decay we know is MAB plus FRB, which is, and what is really interesting to see that no matter what you do, from a question 2 and 3, the power of the engine is numerically FSB, right? Very interesting. So definitely the friction in this case will be more than the before case, but what we need to understand is it should not confuse you that friction is providing power. No. So engine will provide the power equals to this value numerically like this. So what is something crucial to remember is the energy source and who is giving, who is taking away. So it is, you can also think in this way that if I am producing power at this rate by burning fuel, and if you are consuming this energy, then the remaining energy will rate change the kinetic energy of car. So for non-accelerating vehicle, for non-accelerating vehicle, what do you think? Decay will be 0. Then and this is something very interesting for me. You know why? Because even if you're driving a car at constant speed, the engine has to consume energy to work against the drag force. And drag is not zero. So the moment you take away the force from the accelerator, you can clearly see even on a flat surface, but in horizontal load, car will slow down. So it will slow down due to the drag force. Is this clear?
Yes, sir.
So most of the you can say car manufacturer who design car, the fast moving car, expensive cars, they have to take care of the aerodynamics a lot. So car which can go to 170, 180, 200 km per hour, they must have very good aerodynamics. Lack of aerodynamics will eat away the mileage. So you see every car, they mention that if you drive at this particular speed, it will give you the best mileage. And if you drive beyond this speed, the mileage will decrease. The reason is the drag is very random in real life. Drag is not a constant force, rather a dependent force. Okay. So this is the end of work energy power, but I'll teach you separately the idea of vertical circular motion. So I'll keep as a separate lecture, vertical circular motion, which is entirely on this concept on energy conservation and laws of motion. And we'll solve a few problems in vertical circular motion. It's a very interesting topic. And it will take maybe 2 lectures maximum. And then we start the chapter called center of mass. So very soon we are going to reach the rotational dynamics. And once we complete the rotational dynamics, we can go to the class stage immediately. And we'll talk about this later on. So I'm keeping the lecture short because the topic is over. My throat is not functioning really well. So see you in the next lecture.